Okay, like I just mentioned, we'll go ahead and get started. There are some compounds up on the board. I would recommend that you write them down, and we will go over them before the end of the hour. So I'll just go ahead and hit pause here rather than just listening to the awkward silence. So as we had mentioned, and then leave maybe some space to the right or underneath them. And before the end of the hour, we'll go over these. That's how we want it written, but I'm going to, it looks better. Okay, does everyone have these wrote down that's going to choose to do so? Okay, so we'll go ahead and get started. So where we left off with last time was as follows, and that was dealing with bonding. And you have had a paper that was handed to you, and your task is to satisfy the octet rule for each and every one of those atoms. And we'll have some time for you to work on that before the end of the hour. So not each and every element on the table is going to form, as you can see, a single bond. Multiple bonds can also form, okay? So these elements can do double bonds, okay? And we've illustrated that very briefly, and there's probably some examples like that on your paper, okay? And then it is these two that can also do, as you can see, triple bonds. We had left off with that last time. And we did some examples of some triple bonding, and there's some examples in your book if you had, maybe you noticed that already. But moving forward then, okay, what you had done to start the class period is you started writing down different types of formulas, okay? Sometimes you have the formula, then you write the name. Then other times you'll have the name of the compound where you will write out its corresponding formula. So a lot of this is based off of content that we've talked about. Remember I said we're beyond doing examples where we show the Bohr model and maybe there's 2 valence electrons in this outer energy level. So to become more stable, elements like beryllium, magnesium, calcium, strontium, barium, all of those elements being in column 2, having 2 valence electrons would give those 2 away. So once you have 2 less electrons than protons, you have a positive 2 charge. And we've illustrated that multiple times. Well, I don't know if it's multiple times, but I would think that we can probably say we've seen this probably half a dozen times, 6 to maybe 10 times we've illustrated that. And that's not even counting that of doing the Bohr models when you're evaluated on that last chapter. So do we see a theme taking place here? As you go from left to right, what is happening with the charges that you see? They're increasing, but they're increasing how? What is it telling you here? So we're starting in column 1. What type of charge? Okay. Then as you go to column 2, then 3, and then finally 4. So then what happens is just picture climbing up a hill, if you want to look at it that way. Okay. So it's increasing in positive charges. Now you don't need to write this down. Well, this is just for an illustration. Okay. Then eventually you reach the pinnacle and then you go down the other way. So it's increasing in positive 1, positive 2, positive 3, then up here is positive 4. It's making a trend, then it's going to start going back the other way. Now we see negative 3, negative 2, and then -1. So that is the trend that you see in each period on the periodic table. As you go from left to right, you're increasing in positive charges until you get to column 4. Then you start going the other way. Yes, yes. And then you start going the other way where you're decreasing in charges. Okay? No, we said this was just illustration purposes. Okay? Well, you can, but I said you don't have to write that down. All right. So just like we had illustrated, is that you're going up that hill, +1, +2, +3, +4. Then once you get past the hill, now you're starting to go back the other way. Column 5, it wants 3 electrons, so it's a -3 charge. Then in column 6, you get -2 charge, and then finally your halogens. Now, there is an exception to that, and we'll explain what that means at a later time, whether that's today or maybe later down the road. So I know we're winding down as far as your handout is concerned, because I see we're on, it says number 16 of 18. And again, the reason that you write this down is one of two things. It helps me explain that content to you. And then also, when you write things down, I think that reinforces the concepts that we're talking about for those of you who are choosing to fill this out. Here. This one, yeah, we might as well just wrap this up today. I think that'll be all right. Don't forget, we have an evaluation tomorrow. So you also have some terms that are also due. We've had lots of time to work on that. Let's see here. Is that right? That page number, I do believe, is not correct. That is getting multiple charges. So we're looking at polyatomic ions, or no. This should actually probably say 566, not 616. So it is table 2. So page 566, and we'll be looking at that in just a moment. Okay, and then finally, I don't think there's hardly anything to write here, and there might be. Is maybe when more than one element forms an ion, that's essentially what a polyatomic ion is, and these should be little subscripts, and hopefully it shows up like that on your handout. So it should be capital C, capital O, and then subscript means just a lower number like what you would see there. These are subscripts, like that, okay? Okay, does everyone have this content that wants it? No? Still writing? Okay. So, what we were talking about earlier, okay? What we see here is, I want you to think about is, what is at the top of column 5 on your table? Would be, which element is at the top of column 5?
Nitrogen.
Okay, so if you had nitrogen only, you're looking inside that box. So it's going to say its atomic mass of 14. It's going to have the letter N. It's going to say nitrogen. It's going to say a number of 7 for its atomic number. But in the upper right-hand corner, there should be some charges on there. And if nitrogen was alone, it would have what type of a charge? A negative what? What negative charge do you see inside that box? There would be a -3 charge, but that might not be the only one. What else might you see inside of there?
+3 and +5.
Okay, so +3 and +5, okay? We'll come back to that in just a moment. You might be thinking, well, how can we have nitrogen being a +3, a +5 charge, and a -3 charge at various times? We'll explain that here right now. Okay. So when it comes to writing these formulas, okay, what you're going to want to do is write out what the charges are, because we want those charges to add up to what number would you guess? And it's just a guess.
4.
Not 4.
6.
No. Nope. 8 would be your octet rule. That is correct. But in this case, we want the charges to possibly add up to what number?
0.
To 0, which means you have a positive ion and a negative anion. Okay? So, what we see here, oxygen, it has only one charge that we're concerned with, a negative charge of what?
2.
It has a charge of -2. Okay? So then silver, element 47, has a charge of what?
+1.
+1. So notice that these charges do not add up to 0. Okay? So we need to change that formula a little bit. An example that you're very well familiar with would be, for instance, the formula for water. Okay, now you don't need to write this down. We're just making a comparison here. Because what is the charge of oxygen again? Negative what?
2.
And then hydrogen has a charge of positive what?
1.
So notice our charges are the same. They're the same here. So what do we know the formula for water is? A lot of you are going to the drinking fountain or you're washing your hands. What is the formula for all of that water? H2O. So how would we get to H2O from something like this? Well, remember, we want the charges to add up to 0. Because right now we've got a deficit of -1. If you add those two numbers correct together correct, you would get -1, right? Okay? So we divide by the least common multiple, not the least common factor. Least common factor is 1. The least common multiple then is 2, and that goes on top in the numerator, okay? And this is not a value, it's just saying this has a negative charge, okay? So what that means then is what happens when you divide these two numbers? When you divide them two, not subtract. Okay? When you divide 2 by 2, what do we get? 2 divided by 2.
2. 1.
2 divided by 2 is just 1. And we've got 1 here. Then what is 2 divided by 1? What's 2 divided by 1?
2.
Okay? So that's how we arrive at that formula. Okay? So I know we've got construction going on. We're well aware of that. Okay? So then let's do the same application here. What is your least common multiple here?
2.
So then there's nothing wrong with doing this. The answer that you get tells you what to put below. What is 2 divided by 2?
2.
What is 2 divided by 2?
-1.
What is 2 divided by 2?
-1.
What is 2 divided by 2? 1. Okay? We said this is just a charge. It's not the value. Okay? So then 2 divided by 2 gives us 1, which we have. 2 divided by 1 gives you.
2.
So then the answer you get, you put below. For our purposes, I would recommend always starting with your negative ion. Always start with your negative side. Okay? So then, as we continue, what would the name of that compound be? Well, you start with the first element we see, which is what?
Silver.
So silver. And then what happens is it's not silver oxygen. Okay? So I want you to do now is Gesundheit. Open up to page 567.
7.
No, make that 565. 565. Okay? Okay, where it's written in blue, it says writing chemical formulas, okay? And it starts out, does the table in figure 16 look like it has anything to do with chemistry? And of course, I think we would agree, well, no. It is the early table of the elements made for alchemy, a practice from the Middle Ages that laid the foundations for modern chemistry. Alchemists used symbols like these to write the formulas of substances created when the individual elements combine. Before you can write a chemical formula, you must have all the needed information at your fingertips. What will you need to know? So oxidation numbers. To write a chemical formula, you need to know the elements involved. So we've done that. Here are two elements, silver and oxygen, okay? And the number of electrons they gain, lose, share, or to become stable. This last piece of information is what chemists refer to as the element's oxidation number. These charges are the oxidation number because what we see happening is oxygen will gain 2 electrons. That's why it's a -2 charge. Silver will give away 1 electron for every element that you have. That's why there's 2 silvers then. Okay? For ionic compounds, the oxidation number is the same as the charge of an ion. For example, the sodium ion has a charge of +1 and an oxidation number of +1. Then notice it doesn't say chlorine. Chlorine is stable. That is a diatomic molecule. It says a chloride ion then has a charge of -1 and an oxidation number of -1. Okay? So what that means then, we just said what does chlorine have for a charge?
Negative, +7.
Okay, we just read it in the book. At the very bottom of page 565, what does -1? A chloride ion has a charge of -1. Lithium is in which column on the table? Where's lithium located?
The first column.
It's element number 3. So since it's in the first column, what charge does that have?
+1.
+1. So do these charges add up to 0?
Yeah.
Yes, it does. So we don't need to change anything down here. So element 3 is called what? What's element 3 called? Lithium. And then it's not lithium chlorine. It's called lithium what? What did we just read at the bottom of page 565? Lithium chloride. Okay? The reason we say that is if you say pass the salt, which is fine, what is table salt called? It's sodium what?
Chloride.
Sodium chloride. You don't say sodium chlorine.
Pass the sodium chloride.
You can say pass the sodium chloride. So if we take this content here, okay, chlorine is chloride. What would you guess oxygen is then when we write this over here? It's not silver oxygen,
Oxidation.
silver oxide. Okay? Do we catch on to the pattern? The positive side doesn't change. Sodium, lithium, potassium, it's just how it appears on the periodic table. But with negative charge compounds, you change the name just ever so slightly. You drop off the last few letters. Well, let's go ahead and take a look at that. Notice we don't say this. Okay? It's not silver oxygen. You drop the suffix in silver oxide. Okay? So that's how we arrive at that. We don't say lithium chlorine. Okay? We drop these 2 letters and then we say lithium chloride. Okay? Front row, are we on the bus so far? Middle row. Middle row. Back row. Okay? So then, let's see here. Go ahead and turn to page 566. Oxidation numbers and the periodic table. Okay? Many elements have one common oxidation number shown in figure 17. Notice how they fit in the periodic table groupings. Okay? So many of the transition elements have more than one oxidation number as shown in table 2. When naming these compounds, the oxidation number is expressed in the name with a Roman numeral. For example, an oxidation number of iron with an iron 3 charge means you put the Roman numeral 3 in parentheses for a positive 3 charge. Okay? So binary compounds, binary ionic compounds, sorry. The easiest compounds to write formulas are binary compounds, which are composed of 2 elements. When writing formulas, remember that although the individual ions that make up ionic compounds carry charges, the compound itself is neutral. For example, lithium fluoride is composed of a lithium ion with a +1 charge and a fluorine. Notice it doesn't say a fluorine atom, it says a fluoride ion with a -1 charge. The positive names do not change. It's the negative sides that change. Okay? So then one of each ion put together makes a neutral compound with a formula of LiF, or lithium fluoride. Some compounds require more figuring. Aluminum oxide contains an aluminum ion with +3 charge and an oxide ion, and we know it's oxide. We've established that up here. It's not aluminum oxygen. It's aluminum what? What did we just say?
Aluminum,
And?
chloride,
No.
chlorine,
No.
fluoride,
No.
fluorine,
Aluminum what?
Ion.
fluoride, fluorine. I tried anything.
Aluminum oxide. Okay? So, some compounds require more figuring. Aluminum oxide contains an aluminum atom with a +3 charge and an oxide ion with a -2 charge. To determine the overall positive and negative charge, you must find the least common multiple of 3 and 2, which is 6. Again, not the least common factor, the least common multiple. In order to have a +6 charge, you need 2 aluminum ions. In order to have a -6 charge, you need 3 oxygen ions. This gives a neutral compound of Al2O3. So, writing formulas, okay? It says, once you found the oxidation numbers and their least common multiple, you can write the formulas for binary compounds by using the rules below. Write the symbol of the element that has the positive oxidation number or charge. All metals have positive oxidation numbers. Hydrogen often does. So we go by +1 for hydrogen. Write the symbol of the element with a negative oxidation number. Nonmetals have negative oxidation numbers. Hydrogen does occasionally bond to a metal. It's called a hydride, but that is more so with a chemistry, a junior level chemistry class, not at this level. Find the least common multiple of the charges of each ion. The charge without the sign of the ion becomes the subscript of the other ion. Reduce the subscripts to the smallest whole numbers that retain the ratio of the ions. Okay, so as we continue, my suggestion is to always start with your negative ion. Okay, so what does bromine have for a charge?
Can I go to the bathroom? What's that?
No.
-1.
-1. What does aluminum have for a charge?
+3.
+3. Does this add up to 0?
Nor.
Okay. So what would your least common multiple for this be?
1.
No, that's the least common factor.
3.
It would be 3. So then, again, the answer that you get is what you put below. You don't have to do this every time. So what is 3 divided by 1?
-3.
Okay, so we'll just put 3 here. What is 3 divided by 3?
1.
And we've got 1. So let's name this. Al is what? Aluminum. And what is our negative ion called?
Bromide.
It's bromide. It's not aluminum bromine. It is aluminum bromide. Okay? What does the chloride ion have for a charge? Negative what? -1. Just like bromine. Okay? And, okay, we don't have fluorine over here. What does calcium have for a charge?
+2.
+2. These do not add up to 0. So what is your least common multiple?
2.
Okay? So then 2 divided by 1 is 2. Again, that's just a charge. It's not assigning a value. Okay? Then what is 2 divided by 2? 1. And we've got 1. Okay? So Ca is what?
Calcium.
Okay, so calcium,
Chloride.
calcium chloride. Okay. Back row. Are we on the bus here? Front row. And middle row. Okay. So now, sometimes what happens is you can have elements with multiple charges. We just talked about iron. We just read that in the book. Although we don't have iron on here, so let's go ahead and name these compounds. Okay? So we know chlorine has a charge of what? Negative?
1.
Okay? And how many of them do we have?
2.
So there are 2 negative ions on this side of the compound. So that must mean the positive ions would have to be what to add up to 0? So if this is, just picture it like this. This side of the compound is negative 2. So this side of the compound must be positive what?
4.
2.
Positive 2. Okay? So what you had done is when you look inside the box for element 50, what is element 50?
10.
And tin can have what type of a charge? It's positive, but positive what?
2.
Or
4.
it can be 2 or 4. So we know, excuse me. So we know that this is tin. We've established that. So we're going to leave a space because this is a transition metal or has an element with more than one charge. So what is the negative side of this ion called?
Chloride.
Chloride. So now we need to decipher, does this tin have a charge of +2 or +4?
+2.
So then we put parentheses around here, and our Roman numeral for 2 would possibly be what?
II.
2 I's. Okay? Because, excuse me, as we go forward, this is Roman numeral 1. We've established that. That is 2. How do we do Roman numeral 3?
3 I's.
Okay, what about 4? What about 5?
B.
Okay, and 6?
BI.
We typically don't get much past this, but if we were paying attention to last Sunday, well, that's not right. Well, the letters are right. What is the number? And maybe they don't do this either. Maybe that's more accurate. That is Roman numeral what? Do we know?
19.
Nope, because L is 50. What is X? Do we know?
That's a 10.
That's a 10, and we know that that is a 1, and since that is on the left-hand side of this, we subtract. So we just watched Super Bowl 59. Okay? All right. So, what is PB now? Yes. Yes, go ahead.
Hitler. Lead. Lead.
Okay? So, element number, what is it, 80?
82.
82. So that is lead. How many charges does it have? Just one or multiple ones?
4.
So it can be plus what or plus what?
+4. +4.
Okay? So we'll just put parentheses in there because we don't know for sure. But the negative side here, bromine has a charge of negative what?
4.
Well, just one bromide ion.
-1.
-1. And how many do we have? So this whole side has a charge of -4. So what must this lead have to have a charge to add up to 0?
Positive 4.
+4. So then we've got lead 4 bromide. Okay? Why don't you try this one? Chromium, I believe, is what? Element 24, 25, somewhere in there. So we'll just go ahead and hit pause here for a moment. Okay. Does anyone have an answer for this then? Yes.
So on the chlorine side, it's a -1.
Yep.
And the other side is +3, and that would be -3. So chromium 3 I's
Okay.
in parentheses chloride.
That is correct. This one's a little more difficult. Maybe we're running short on time. We'll come back to that because it has a polyatomic ion. Because in class, we said a polyatomic ion means you can have more than one element that acts as a single charge. Okay? So then we never got a chance to talk about nitrogen having a positive charge. We can get to that tomorrow. Okay, so you have just a few minutes left. Is there anything on that paper that you're looking at that I just don't quite understand?
This one,
It is C2 what?
H4.
C2H4. Okay? Is anybody having a problem with this paper? Okay, well, we had one question, so we'll go ahead and answer that. So the logical approach that you would probably take would be this. I can explain this in a moment. So now we're past this. The single bond isn't working. So then you had correctly said, well, this logical approach of a single bond isn't working. So let's try a double bond then. And this is how you would illustrate that. These electrons, they're being shared. So there's still 2 X's left here and here, a triangle here, and a triangle here. So then wherever did you see an X or a triangle, what could you put? Because how many hydrogen atoms do we have? Okay, so we could put a hydrogen atom here and a hydrogen atom here. Now, inside this box, how many electrons are there? How many E's, X's, and triangles are in here? There's 8. So this carbon is now stable. So then you would do the same thing here. And then how many electrons are inside this box now? Same thing. There's also 8. Okay, so we will pick up with this next time.